You clicked on this video because you have likely started a data project that never seemed to finish. You are probably frustrated that your model training hung, your cloud bill exploded, or your infrastructure simply refused to start. The stakes are real because these failures are costing you time, money, and your confidence as an engineer. Here is the insight you will get by watching. The problem is rarely your code or your data quality, but a fundamental mismatch between your naive project scope and the physical limits of the hardware you are trying to run it on. Most engineers approach data projects with a logical assumption that if the algorithm is sound and the data is clean, the system will simply work. This is a dangerous mindset because it ignores the physical reality of how artificial intelligence actually runs. When you write a script to process a dataset, you are not just writing logic, you are making a request to physical silicon. That silicon has strict limits on how much data it can hold in its memory and how fast it can move that data around. You might assume that if you have enough compute cycles, the job will finish. But compute cycles are useless if the data cannot reach the processor fast enough. This is where the first major failure point hides. Consider the architecture of modern GPUs and TPUs. These chips are designed with massive parallel processing power, but they are starved by a much smaller memory bandwidth. Think of the GPU like a Formula One race car engine. It can rev to incredible speeds, but it needs a constant high-flow fuel supply. In data projects, the fuel is the data itself. If your project scope assumes that you can simply load a massive dataset into memory and start training, you are assuming the fuel line is infinitely wide. In reality, the bandwidth is finite. When you try to feed more data than the memory bandwidth can handle, the processor sits idle waiting for information. This is known as memory bandwidth saturation. The hardware is powerful, but it is effectively paralyzed because it cannot get the data it needs to compute. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This creates a specific type of failure that looks like a software bug but is actually a hardware bottleneck. You might see your training loop spin slowly, or your inference service time out, and you will instinctively look for bugs in your code. You might rewrite your loops, optimize your data loaders, or try to clean your dataset further, but the code is fine. The issue is that your project scope assumed linear scaling. You thought that if you double the data, you would just need to wait twice as long. Instead, you hit a hard wall where the data movement costs exceed the compute gains. The model never trains because the hardware is starving for data, not because the math is wrong. Now consider the mechanics of stopping and pausing projects in modern cloud environments. You might use platforms like Supabase or DataLab to manage your workflows. These tools are designed with a specific philosophy in mind. They treat workloads as ephemeral and stateless, meaning they expect tasks to start, finish quickly, and then disappear. This works beautifully for web servers or batch scripts that process a file and then exit. But large-scale AI workloads require persistent, high-bandwidth memory states. They need the hardware to stay allocated and ready to receive continuous streams of data. When you try to run a massive model on a platform designed for short-lived tasks, the infrastructure fights against your needs. The system might pause your project after a period of inactivity, or it might force a deletion because it thinks the resource is idle. This is not a policy failure, it is an architectural mismatch. The tools are built for batch processing, but you are trying to bridge that gap for continuous, high-bandwidth AI inference. This brings us to the core of why so many data projects fail before they even begin. The barrier to starting a data service startup is rarely an algorithmic one. You do not need a new mathematical breakthrough to get started. The barrier is the realization that the shiny object of a new model requires hardware density and bandwidth that exceeds the naive cost models used to scope the initial project. When you plan a project, you often calculate costs based on the number of hours a machine runs. You assume that if you rent a GPU for 10 hours, you get 10 hours of useful work. But if your project scope does not account for the physical constraints of memory bandwidth, you might spend those 10 hours in a state of constant waiting. The machine is running, but it is not working. You are paying for compute that never gets utilized. Resource leakage in stopped projects is often a symptom of this deeper issue. When a system is built for batch processing, it cannot sustain the continuous memory residency needed for AI without immediate hardware reallocation. If you try to pause and resume a high-bandwidth workload, the system often has to tear down the memory state and rebuild it. This process consumes resources and time, leading to the perception of inefficiency. But the root cause is not the billing or the policy. It is the fact that your project scope assumed the hardware could handle the state persistence without the necessary physical density. The failure is a bandwidth starvation event where the project scope assumes linear scaling of compute, but the underlying hardware hits a hard wall on memory throughput. The most valuable insight here is that you must stop thinking about your project as a software problem and start treating it as a physical engineering challenge. Before you write a single line of code, you need to ask if your data volume and model complexity can actually fit within the memory bandwidth constraints of the hardware you are using. If the data movement costs exceed the compute gains, no amount of code optimization will save the project. You need to align your scope with the physical reality of the silicon. This means potentially simplifying your model, reducing your batch sizes, or choosing a different hardware architecture entirely. It means accepting that the shiny object might be too heavy for the infrastructure you have available. This shift in perspective changes everything. Instead of chasing bugs in your code or blaming your data quality, you start looking at the physical limits of the system. You realize that failure is often a bandwidth starvation event where the project scope assumes linear scaling of compute, but the underlying hardware hits a hard wall on memory throughput. By acknowledging this, you can design projects that are physically viable from the start. You can avoid the trap of building something that looks great on paper but collapses under the weight of its own data requirements. The difference between a failed project and a successful one is often just this one realization, that the machine has physical limits and your scope must respect them. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.